Hi, and welcome to episode 2 of Cartography. And joining me, Kenfield, today is John Nelson and Wes Jones. And we're going to spend, hopefully not too long, because we don't know much about this, talking about maths for Mapmakers.
Maths. It's plural?
Well, I'm just British, what can I say? It's maths to me.
Okay.
And it's math to you, right?
I'll go with math.
And where's your Canadian?
I will split the difference and say
Of course,
math.
you're Canadian.
Like a long A. Math.
Yeah.
Okay, so we're going to be talking then about numbers and how they relate to making a map. If we're going to talk about Earth, I guess we should see it. Shall we?
Let's check it out.
Let's get an Earth. Okay, so we've got a few globes here, but let's just use this one for reference. This is a great old globe, actually.
It is.
Should we get some facts out of the way first? How big is this object?
I'd say it's about 11 inches in diameter.
It's a roundabout. And at what scale is this then?
1 to 6 million.
Is it? I don't know.
Oh, I don't know.
What's the circumference?
30,000 clicks.
Well, off the top of my head, it's 24,900 miles in circumference.
24,000?
24,900
That's
miles.
what I was going to say.
Around the equator. So, okay, that would be easy then if the planet is a ball shape, right? Because you would then make a fair assumption that it's the same distance on the meridial axis, yeah? Mm-hmm. But we know it's not.
It's not, yeah.
So what's the distance north to south and around?
Oh, the actual distance. So
Smaller?
it's 24 wide, so it's 22 around.
Well, small is good enough, right? Yeah. It's 24,812 miles that way, right?
I was just kidding about the 22.
So here's the interesting thing about the planet. It's 14 miles shorter in distance if you go through the poles that way than it is around. And that gives it its own shape, right? And we call it an oblate spheroid because it's kind of squashed.
Because it's this ball of lava in space spinning, right? So it's
Yeah.
going to be squished out at the edge just a little bit.
Correct. Yeah. It looks a little bit like me. Kind of short and a
I
little
don't believe
wide.
that.
Well, that's, it's been said. So this creates a bit of a problem for making maps because it's not a perfect sphere. It's not a perfect ball. So spherical geometry and maths doesn't work. So we're going to spend a little bit of time thinking about how do we get this huge object that's mathematically pretty difficult to work with, how do we get it onto a small sheet of paper or a screen or a mobile device? And what are the issues of transforming from a roundish kind of odd-shaped object onto something that people can use on their mobile phone every day?
It's somewhat tricky because even though we've talked about how it's not even a perfect sphere, so you've got to put that into almost a perfect sphere, which is a geographic coordinate system, and then take that into a projected coordinate system.
So conceptually, we're taking this weird shaped thing, which is kind of a sphere, and we're wrapping it in a grid. And the lines that go up and down are called longitudes, and they come to a point in the North Pole, and they come to a point in the South Pole. And then the lines that go up and down are lines of latitude. So I always remembered latitude like you climb a ladder, the rungs of a ladder. I go up a ladder, and I can go down a ladder. Latitude tells me how far up or down something is. And longitude, I think of as being how long around is it, right?
Yeah, and I always thought of them, they're all long lines. So every single one of them is a long line, so that's how I remember longitude.
Yeah. And to describe the position of a place, all you have to do is say how far up and down it is and how far east and west it is. And the intersection of that is called a coordinate. A coordinate.
So I've learned something. I've learned that latitude has D's in it, not T's.
Latitude.
Who knew?
Latitude.
And really, all you're doing is taking the coordinates for anything on the globe and then translating them mathematically onto a piece of paper. But let's get back to a little bit of the conceptual things, like thinking about, forget the maths, it's hard.
No problem.
Let's think about wrapping objects around a globe. How would you do that, Wes? What sort of ways would you?
There's a few different ways that people typically do them. One is with a cone. So you put a cone here and it comes out, and you project that Earth onto the different parts of the cone. That's one way.
So like a dunce cap.
Exactly,
sitting
like
on
a
the
dunce cap. And you can put it in different spots. You can have the dunce cap over here if you want to preserve more area in this, or more aspects of the Earth in this area. You can put it over here. You could take a but like basically a plane, a piece of paper, and you put it almost through the Earth. And then it gets, again, projected into different parts of that piece of paper. You can also take, a very common way is a cylinder. You just put it through. And again, the Earth just gets projected onto different parts of that cylinder.
Yeah, and these give us our three major families of map projections: conic, azimuthal, and cylindrical. If you hear those terms, that's essentially what they mean. It's just about imagining the projection of the lines of the graticule and the coordinates of the objects you're mapping onto these shapes. And of course, if you wrap a cylinder around here and you then take it off and unfold it, you have your flat map. Okay, what about this orange peel?
Well, you can think of the Earth as an orange like this. And in order to smash this peel, I mean, something has to give, right? I'm going to distort the size of something. I'm going to distort the direction of something as I smash it down. And I happen to have peeled an orange already.
Wow.
Magnificently. And it looks a little bit like this.
Take 23?
Which is sort of like what this globe would look like if we popped it off its hinges and flattened it out. It would have these fingers that had been separated so that they could all conform into a globe again. And a flattened projected map is a flat version of something that was originally relatively spherical. And when you flatten it out, there are compromises that you have to make. These guys up here kind of took one for the team. But if this is the equator, then that's going to be reasonably accurate in my projection.
So you're making tears and you're squashing.
Yeah. So
And these create distortions. But there are some other sort of properties, I guess, of a map projection that cause problems for map making. So let's think of a few of them. Distortions in area. Distortions in
Distance.
Yeah.
Distortions in
you've got direction.
directional.
And size.
Definitely
Yeah.
size.
So you end up with all of these different problems and these different compromises that you need to wrestle with. Thankfully, software does a lot of that hard work for us and hides the maths behind the scenes. So the job of a modern cartographer is really more about choosing an appropriate projection. So maybe Wes, if we deal with Webmaker as an example, talk us through some of the problems or the positives even.
It's got a lot of problems and positives, the Web Mercator, because everyone gets on Web Mercator being, oh, it's just a horrible, horrible projection. But it does a lot of things really well, actually. Like, if you're using it for navigation, it does a great job at navigation. That's its main purpose. And so you can see there's a reason why that map became the kind of de facto map, because it started kind of as a navigational map. One thing it does quite poorly is because it distorts things, especially in the northern and south, so much that you can't really get a good sense of what the area is. So you could have a place like Greenland here, which you can see it in the globe. It's a humongous island, but it looks bigger than Africa, and it's just not the case. So that's one of the things it does wrong. And I don't even know actually if Web Mercator or Mercator actually ends at any point. I think it goes to infinity.
Yeah.
So,
mathematically.
So if you had something at the very top, it would actually technically go forever.
Wow, that's a big map. But there are thousands of projections, and it's really about making a choice. So when you're choosing maybe a map to present population-based data, John, what would you go for?
I would definitely choose something that maintained area.
Okay.
So if I'm mapping percentages or raw numbers on a map, and I want to be as impartial as possible, if I make a small place look very large compared to other places, there's an inherent bias there that affects my interpretation of that map. So I'm going to do my best to look at the projection's weaknesses and its strengths and say, I'm going to choose one that maintains area.
So we've just really introduced the idea that numbers and maths is really quite difficult, and let's let the software do a lot of that hard, heavy lifting, but having some awareness about the choices you make and making sure those choices fit the purpose that your map is intending to show is the key thing in today's cartography.
Picking a projection is actually super fast in a lot of these tools, right? I can change a projection and see what the impact is, pick another projection, see what the impact is, and it's a lot of fun, too. I mean, mapping is fun, but picking a projection is a lot of fun, too.
You notice that both of us started smiling when you were saying changing projections was fun.
I think it's fun.
It's pretty fun. We're going to be looking at a very famous map by the French engineer Charles Maynard, who made this map in 1869, depicting Napoleon's march to Moscow of 1812.
What I appreciate most, perhaps, about this map is that it shows a geographic phenomenon and it shows a charted phenomenon at the same time. And you get different insights from a non-geographic charted element than you do with a geographic element. But when you put them together, it becomes more than the sum of its parts. You get these cool insights that happen when you combine charts and maps.
Yeah.
And I think part of that is because it looks so much like a chart, it has a really appealing aesthetic to it, and it really draws you in. And you start looking at it, and you're like, oh, this is really interesting. You can see as this army went further towards Moscow, more and more people died, and you can see that in this chart form, but it, like you said, ties in that geography, so it's a really fantastic
It's very Spartan, so there's nothing on that map that doesn't need to be there.
Exactly.
It's almost a non-map, right?
Yeah.
I mean, it's the least map-like map there is, I think, but it's so effective at what it does. And if you break it down, it's like one line.
Yeah.
That's it. It's a single line, and it's depicted as a flow, and it has a thickness that says, here we have 400 and so many troops, and then the line slowly gets narrower and narrower as it gets to Moscow, and even further still, and you end up with an absolutely decimated army.
And that same line is represented temporally in the chart by a degree. So how cold was it during this march? And as that line plummets in your chart, it also gets much thinner in the map, and it's remarkable.
Yeah, and that's how a lot of the troops died. This is the middle of winter, and they froze to death. This is why it's an anti-war thing. So it's a flow map, and it's a classic example of the flow
Of
map.
never getting into a land war in Asia.
Do not follow Napoleon anywhere. No. I think is the key to that one. Beautiful map.
Aristotle?
Aristos.
So what I thought for person of the week this week is we'll look at the work of Eratosthenes.
Eratosthenes.
Yeah.
Eratosthenes.
Yeah,
Eratosthenes.
that's it.
Got it.
Okay, go
5
on.
syllables.
What do you know about
Eratosthenes.
this guy?
A genius. One of the fathers of geography. How big is this world that we're on? Which, by the way, was known to be round at the time, hundreds of years ago, actually thousands of years ago. Eratosthenes. And he noticed that when he looked down a well, he saw his shadow cast perfectly down to the bottom of the well on the equinox. Given that information, he traveled 500 stadia north, and at the exact time that his shadow would have been cast perfectly straight down a well, he measured the angle of a tower of known height. And given that angle, he could say, well, if it's this many degrees, which was, 7.5 degrees or something like that, and he duplicated that inside a 360-degree circle, he determined that the Earth was
200
really close to what it actually is, a couple thousand years ago.
Yeah.
Really close. He's using his head, and then he's applying a little bit of math to that.
And then they forgot all that, right?
Yeah, they forgot it.
Yeah, and we use computers now to do all that, so, but very impressive work. What's his name?
Eratosthenes.
There we go. This week's tool of the trade. Drum roll. Okay, let's see. See what the magic box has got for us this week. And what is that?
A horseshoe.
What is that?
A licorice stick?
So another tool of a bygone cartographic trade.
It's heavy.
It's got a little weight to it, yeah.
Is it lead?
No.
I bet it is.
You can bend it. though.
Hey, look at that, you can bend it. So what would you use that for as a cartographer?
Paperweight?
So drawing straight lines is pretty simple. Okay, you get a ruler, right? And you draw your straight line, and then you move your ruler and you draw on a straight line. But what about curves? We've dealt with
Curves are hard.
maths
It's
in
hard to
this
draw a good
episode,
curve.
and we know that the Earth is a roundish shape, and we've got a lot of curves to put on the map. How do you draw a curve? So this is a flexi-curve.
Made in England.
Yeah, look at that.
And you would manually trace this line
You would.
on your paper map?
Yeah, I know. And you sometimes use these instead. This is a set of French curves. And so you would move these around your paper and trace.
These I know because you use them a lot in art too, and in woodworking, and you can kind of look around here and get kind of any curves almost you want. Like even here, this is a different curve than this one, the angles of it. It's working with different radius around the French curves.
So now in a digital environment, you know, you put two little points down and you grab some handles and you make a nice
drag those splines around.
Bezier
That's how you
curve.
do it.
And this is how you used to do it. Yeah?
Wonderful.
Yeah. Tool of the trade.
French curve.
And finally this week, let's turn our attention to some of our favourite carto fails, pet peeves, things to look out for and possibly avoid. Yeah, and if we're thinking about the maths for map makers and we think about putting graticules and scale and north arrows on our maps, what are some of the problems, pitfalls that we fall into? John?
Doing it every time. Having a checklist. This must have a scale bar. It must have a north arrow. It must have graticules. Thick, fat graticules. So how important is it to actually show a graticule on your map? Not terribly important in a lot of cases. And if it is terribly important, it still doesn't have to be full black, very thick, right? So it's still very obvious if you use a deeper color of your ocean blue for your graticule. And your graticule kind of doubles as a lot of things in this case. So if you have a graticule on your map, which is the latitude, longitude grid reference on your map, you might not need a neat line around your map because it can serve as a neat line. Not that I like neat lines anyway, right? Not that you have to have a neat line.
Right, so for a lot of maps you don't necessarily need a lot of this stuff. What about scale and north arrows?
Definitely don't need scale and north arrow on a lot of maps. And again, like John said, you go through this checklist, you think, well, I've got to have these certain things, especially I find if you're not so familiar and new to cartography, you're like, well, I have to have a bar scale or scale bar, however you call it. And like you look at that Web Mercator map, it doesn't really serve a purpose. It just has to be this tiny little thing in the bottom often, especially because that distance often isn't that important. And that ties into the north arrows. North isn't always up on the map, and do you even need north on this map? And I think a lot of people are with north arrows. They see these really old maps and they're like, well, I want this north arrow because it's super ornamental on it.
Yeah, there's the temptation to have the big flowery north arrow. How cool can
Pirate,
I north?
I
made this north arrow.
Pirate map north arrow.
In my first class of cartography, that's what I did. I said, that's it. I'm going right to the north arrows and designing my own.
Yeah.
But you don't realize that that was done for certain reasons, but aesthetic. But you looked at the rest of the map and it was ornamental. And so that tied into the map where you just don't need that.
Yeah. For me, you mentioned Web Mercator again, and it's going to seem a little bit like we're bashing Web Mercator. But my pet peeve is just simply a map of population data that's on Web Mercator. You know, a web map where it's a choropleth, it's a shaded map, and you know, it doesn't take a lot of effort to choose an equal area projection instead of Web Mercator. Your map readers will thank you for it if you pick the correct projection. And with that, I think we're going to wrap this particular episode. So, can I offer you guys a biscuit?
Thank you, Kenneth.
Thank you.
Chocolate digestive, custard cream, Garibaldi.
Take one of these guys.
Yeah,
Thank you.
Okay. Thanks very much.
Thank you.